With our guided notes for section 4.1, we move on to exponential functions. Now, exponential functions look different from our polynomial functions. An exponential function is what we call a transcendental function. It transcends our algebraic functions that are our four major operations: add, subtract, multiply, divide. If we raise something to a power, where we have a squared function, a cube function, etc., or take the root. So my square root function, my cube root function, these are all the functions that we've focused on so far. With our exponential function, however, now that variable, that unknown, is in the exponent, not the base. And when we have an exponential function, it's going to show a pattern of growth or decay depending on what the shape ends up looking like. So my exponential function, my parent function, is going to be exponential growth. It's going to intercept the y-axis right there. Now you see as I move from left to right, it's increasing. If I reflected it across the y-axis, then that would be decreasing. It would be a decay function. The inverse of my exponential function is what we call the logarithmic function. And we're going to move into those with the next section. Okay, so we have three parts to our exponential equation. We have a base raised to an exponent, and that's equal to what we call an argument. A base raised to an exponent is equal to an argument. For example, if I did 2 cubed equals 8, well, 2 is my base, the 3 is my exponent, and the 8 is my argument. My exponential function definition says an exponential function with base a, so whatever base I end up using, base a, f of x, a to the x, where x and a are both real numbers. So both of these are real numbers, not imaginary. And my base, now notice these restrictions are on the base, not the unknown, not the exponent. My base is going to be greater than 0. Numbers greater than 0 are positive. Positive, not negative. And my base is not going to be 1. Because think about it, if you take 1 and you raise 1 to any power, it's just 1. 1 to any exponent is just 1. So it doesn't follow our pattern of exponential growth or decay. A can't be 1 because 1 to any power, 1 to the x, is a constant function. Doesn't show growth or decay. A has to be greater than 0. My base has to be positive, because otherwise it could end up being imaginary. So think about this. If we had a to the 1/2, if my exponent is 1/2, that means I'm taking the square root. And if a is negative, let's say I've got -2 to the 1/2, I would have the square root of -2. That's an imaginary number right there, because my exponent can be a fraction. That's fine. Or my base could end up being undefined. If I had, let's say I have a to the negative x, well, that when I take that negative exponent and apply it, it throws that a to the x, that value, into my denominator, which means I would have a place where the function is undefined. And you can see that according to the shape of my graph, I can plug in any value of x. My domain for my exponential function is going to be all real numbers. It is limited by a horizontal asymptote. Horizontal asymptotes, you know from rational functions, that parent exponential function has a horizontal asymptote at the x-axis, and my parent exponential function also has a y-intercept at 0, 1. Of course, if I transform that, if I move it left, right, up, down, this horizontal asymptote would move up or down. This point 0, 1 would move, so I could figure out where that curve in my exponential function would be. So let's back up a little bit. Let's talk about and think about our pattern of exponents. We're going to review what the exponents, what happens when we have positive or negative exponents. Okay. So we've started up here with 2 to the -5. We're going all the way down to 2 to the 5th. Let's just start in the middle and see what happens. If we do 2 to the 0, well, hopefully you remember that anything to the 0 power is 1. But if not, we're going to establish why that is as we work through this pattern. Well, 2 to the first is just 2. 2 squared is 4. 2 cubed, 2 times 2 times 2 is 8. 2 to the fourth, I multiply that times 2 again, and I get 16. 2 to the fifth is 2 to the fourth times 2, which is 32, and I just keep going. Because you can see that where my base is 2, as my exponent increases by 1, I'm multiplying the argument by that base. So 1 times 2, 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Because each time I increase the exponent by 1, like 2 cubed is the same thing as 2 squared times 2 to the first. 2 squared times 2 to the first, well, 2 squared is 4 times another 2 is 8. 2 to the fourth would be 2 cubed times 2 to the first. 3 plus 1 gives me that exponent of 4. 2 cubed was 8 times 2 is 16. And that's how I work my way down as I'm following that pattern where my base is 2. Now if my base changed, that means I would be multiplying by whatever that base might be. 3, 5, 7, 16, whatever my base is. So that's how it works multiplying my way down. I'm always multiplying by another value of the base, in this case 2. What if I'm going up? Well, 32 to 16 to 8 to 4 to 2, I'm moving the opposite direction. When I was moving down, I was multiplying by 2. What's the opposite of multiplication? Well, the opposite or inverse of multiplication is division. So 32 divided by the base, divided by 2 is 16, divided by 2 is 8, 8 divided by 2 is 4, 4 divided by 2 is 2, and right here comes our pattern why anything to the 0 power is always 1. 2 divided by 2, 2 divided by 2 is 1, so that's that value right there. Now I'm going to keep walking my way up through that pattern. 1 divided by 2 is 1/2. What is 1/2 divided by 2? Well, 1/2 divided by 2, division with fractions, means I need to multiply by the reciprocal, and the reciprocal of, I did that in my head, and I got the answer and I wrote it down. Let's try that again. I'm dividing by 2, not 4. 4 divided by 2 is 2. 2 divided by 2 is 1. 1 divided by 2 is 1/2. 1/2 divided by 2 is the same thing as 1/2 times the reciprocal of 2, and the reciprocal 2 is 1/2. 1/2 times a half is a fourth. So what's 1/4 divided by 2? Well, 1/4 divided by 2 is the same thing as a fourth times a half, which is 1/8. Are you seeing a pattern going on here? Go ahead and fill in the last 2. Take a second to look at it. Hopefully you notice that, for example, 2 to the 5th is 32. 2 to the negative 5th is 1/32. 2 to the 4th is 16. 2 to the negative 4th is 1/16. 2 squared is 4. 2 to the negative 2 is 1/4. So when I put a negative in my exponent, it tells me to take the reciprocal of the base. Now we are going to write down all of our rules for exponents to make sure you have a place where you can look back and find those if you need them. So here we are on the next page, rules for exponents. First thing, 0 exponent. Anything raised to the 0 power is 1. So it doesn't matter what my base is. 2 to the 0 is 1. 3 to the 0 is 1. Negative 3 as the base to the 0 is 1. So in general terms, anything to the 0 power is 1. Any variable, any number to the 0 power is 1. Now, notice right here I made this negative 3 my base. What if I took those parentheses off? Well, if I take those parentheses off, this is like, my base is just the 3. Here my base is the negative 3. But here my base is just the 3. This is like saying -1 times 3 to the 0 power. That negative is not part of the base here because it's not included in parentheses. Well, 3 to the 0 power is 1, but then I need to multiply that by a negative. So pay attention to whether your base has, if your base is negative, pay attention to whether your base has parentheses around it or not. All right, the next rule for exponents, a negative exponent, tells us to take the reciprocal of the base, and we just walked through some of those on the other side. We did, 2 to the -2, and that gave me 1 over 4, because 2 squared is 4. 2 to the -2 is 1 over 4. If I did 3 to the -2, that would be 1 over 3 squared, which would be 1 over 9. Again, pay attention if you have parentheses around the base. Here my base is 2/3. So that negative exponent tells me to take the reciprocal of my base. I flip it, and now my exponent's positive, and I still raise both of those to that power. So that would give me a positive 9/4. All right, and our final rule for exponents here, rational exponents. A rational exponent is a fraction. To find a rational exponent, you take the root. You're going to use the denominator of the exponent, the bottom number, as the index of your root, and the numerator as the power of your root. Oh, I didn't give you any. Okay, so here in general terms, m to the 0 equals 1. Anything to the 0 power is 1. M to the -1 is 1 over m. So anything to negative exponent, you take the reciprocal of the base. Now we're doing our rational exponents. A rational exponent is a fractional exponent. Let's do 8 to the 2/3. Well, when I see that this exponent is a fraction, I immediately know I've got a radical set up. The base of the exponent is the radicand, the value underneath the radical. The denominator of the exponent is the index. So this denominator of my fraction, my rational exponent, is the index. It tells me which root I'm taking. In this case, I'm taking the cube root. And then the numerator of the exponent is the power. So I'm going to take the cube root of 8, and then I'm going to raise it to whatever that numerator is. I'm going to square it in this case. So here I take the cube root of 8. Well, what times itself 3 times is 8? That would be 2. So I've got 2, and then I still need to square it. The cube root of 8 is 2, and 2 squared is 4. One more example here. Let's do 16 to the 1/2. Well, fraction, rational exponent, I've got a radical. The base goes underneath my radical, my radicand. The denominator is the index. If it's the square root, I don't have to write that index there. And then I'm just going to raise that to the first power. So it's just the square root of 16, which would be 4. A more general look at this, if I have any base raised to a rational exponent, I'm going to go ahead and give you numbers here so there's not 3 different variables involved, because I think it's a little easier to look at. That's my pattern that I'm following. Okay, let's practice evaluating some of these. These are exponential functions, and I know they're exponential functions because my variable is in the exponent. That's what makes it an exponential function. So I've got 4 to the x as my function. Here I need to find f of 3. So I'm replacing x with 3. The x is my exponent, so that would be 4 cubed. Well, 4 times 4 is 16, times 4 is 64. Here my base, or my exponent, excuse me, my exponent is going to be -2 because I'm replacing the x with -2. 4 to the -2 negative exponent tells me to take the reciprocal of the base. I still need to square it. So I've got 1 over 16. And then here I've got an exponent that's going to be rational, 4 to the 3/2. 4 to the 3/2 tells me, all right, I'm going to do 4 as the radicand. The denominator is the index. I don't actually have to put that 2 there, but I was talking and I did. The power is the 3. So I take the square root of 4, that's 2, and 2 cubed is 8. All right, my next one, my exponent here is 2 minus x, so I'm going to take these values and replace the x there. So I've got 5 to the 2 minus 3. Well, 2 minus 3 is a negative 1. Negative exponent tells me to take the reciprocal of the base. Here I'm replacing my x with a negative 2. So I've got 5 to the 2 minus a negative 2. Well, 2 minus negative 2 becomes 2 plus 2. So it's 5 to the 4th power, which is 5 times 5 times 5 times 5, 625. If you need a little help in your calculator, that would be 5. There's my exponent button to the 4th power, 625. And finally, I have h of x is 1/3 to the x. So my base is a fraction. I got to keep track of that. So I've got 1/3 in parentheses to the negative 2. Negative exponent tells me to flip the base. If I flip a third, it's just 3. I still need to raise it to that power. And finally, 1/3 cubed. Well, 1 cubed over 3 cubed. 1 to any power is just 1. And 3 cubed is 27. Make sure you do 3 times 3 times 3, not 3 times the exponent. All right, graphing exponential functions. Now, first we are going to remind ourselves of what the definition for an exponential function looks like. An exponential function says f of x equals a to the x for all values, and then we have those restrictions on the base. A has to be positive, greater than 0. And a can't be 1 because 1 to any power is just that constant function. A is the base, not giving us domain or range. My domain for my exponential function is going to be all real numbers. I can plug anything into that exponent, that's fine. My range is going to be limited by horizontal asymptote. If it's a parent function, that horizontal asymptote is at the x-axis. But if it's not the parent function, then it could move up or down. My exponential function shows exponential growth or decay, and it's much more explosive than polynomial growth or decay. It means it moves up or down much faster than a polynomial function would. That happens because the variable in an exponential function, that variable is in my exponent, not in the base like it would be with a polynomial function. Okay, let's look at some examples of graphing exponential functions and what happens as our base changes. It's just a little bit blurry. I apologize for that. I did my best to try to bring it back together. Now, for these 4 exponential functions that are graphed here, we've got blue, red, green, and black. For these 4 exponential functions, if you can read, hopefully you can, yeah, you can see pretty well, at least I think you can. My base is 10, 3, 2, and 3/2. For each of these, my base is a whole number in the sense that it is greater than 1. This is not a whole number, it's a fraction, but it's a mixed number. It's an improper fraction. My numerator is greater than my denominator. The absolute value is greater than 1. So when I say whole number, it just means greater than 1. But sometimes we don't think about that absolute value greater than 1 as all I'm saying is it's going to be positive, and it's going to be more than, it's going to be at least, well, it can't be 1. It's going to be more than 1. Okay, so let's think about what happens to the steepness of the slope as the base gets larger. Well, I've got 10, 3, 2, and 3/2 as my base. Out of those 4 bases, 10 is the largest, and 3/2 would just be 1.5, so it would be the smallest. So as my base gets larger, so as I move from my smallest base up to my largest base, notice that this curve gets steeper. So as the base gets larger, as long as that base has an absolute value greater than 1, is a whole number, the increase, the curve up, gets steeper as the base gets larger. My increase gets steeper as the base gets larger. Now we're going to calculate some values for each of these functions that are defined on this graph, and I'm going to try to color code them for you. We're going to leave this one out just because raising 3/2 to an exponent is a little more work than the others. We're going to start, let's start here with y equals 2 to the x. So when I plug in values for x, f of x equals 2 to the x. we're going to plug in our 5 basic values. Whenever I'm using exponential functions, there are no magic values, but these 5 are the ones you want to start with because they're going to get you that exponential increase or decrease. You're going to find your asymptote and your increase or decrease a lot faster. I'm going to color code. We've got values of x when f of x or y equals 3 to the x in red. We're still doing those 5 basic values. And then finally, when our base is 10, we've got values of x when our base is 10 and our exponent is x. Same 5 basic values. Okay, so 2 to the x. Well, we just did this on our first page of our notes. 2 to the negative 2 is 1 over 4. 2 to the negative 1 is 1 over 2. Anything to the 0 power is 1. 2 to the first is 2. 2 squared is 4. So 2 to the negative 2 is 1/4, 1/2, 1. 2 to the first is 2. 2 to the first is 2, 1, 2, 4. Oh, they're counting by 2s on our y-axis. 2, 4, 6, 8, 10. So 2 to the first is 2. So yeah, that's right there. 2 squared is 4. And we've got our horizontal asymptote at 0 and our exponential increase. When I do, my base is 3. 3 to the negative 2 is 3 squared reciprocal. So 1 over 9. And then 3 to the negative 1 is 1 over 3. Anything to the 0 is 1. 3 to the first is 3. 3 squared is 9. So again, over here, I've got tiny, gets a little closer, goes through that intercept 0, 1. 3 to the first is 3, up a little further. 3 squared is 9, up a lot further. So we've got this exponential increase. We've got our horizontal asymptote out here toward negative infinity on the x-axis. Horizontal increase, our exponential increase as we move in a positive direction. Finally, 10 squared is 100, so 10 to the negative 2 is 1 over 100. Let's go ahead and fill that in down there. 10 to the first is 10. 10 to the negative 1 is 1/10. Anything to the 0 power is 1. So we've got teeny tiny fractions over here. Goes through our y-intercept at 0, 1. 10 to the first is 10. 10 squared is way off our graph up here at 100. So we've got our horizontal asymptote again. Our horizontal asymptote would be the x-axis. Horizontal asymptote, y equals 0, x-axis. For all of these functions, we've got our y-intercept at 0, 1. For all of these functions that are basically our parent function, no transformations being done. Just the base, as that base gets larger as a whole number, that base increases. Okay, now let's look at decay functions. These were exponential growth functions. Now we're going to look at exponential decay functions. Notice as I move from left to right, my exponential growth functions go up. I'm increasing. My exponential decay functions, as I move from left to right, are going down exponentially. They're decreasing exponentially. And if you compare these bases, you see that they're the reciprocals of the bases on the previous graphs. Instead of 3/2, I have 2/3. Instead of 2, I have 1/2. Instead of 3, I have 1/3. And instead of 10, I have 1/10. So I've taken the reciprocal of those. So when I think about those bases are going to be fractions, right? My value for A is going to be less than 1, the absolute value less than 1. Basically, I have a proper fraction as my base. The value for the base is less than 1. Now, it still has to be positive because that's my definition of my exponential function. What do you notice about the steepness of the slope as the base gets smaller? Well, those bases are fractions. So how does 2/3 compare to 1/10? Well, 1/10 is actually smaller than 2/3. So I have a steeper decay, a faster rate of decay. My slope goes whoosh as that base gets smaller. The base, which is my fraction, gets smaller. And it asks me to calculate values again. So if I color code these same colors, I've got the reciprocal of, we're going to not worry about that one. We've got the reciprocal of y equals 2 to the x. We've got the reciprocal of that. We've got x as f of x equals 1/2 to the x, which would be the same thing as 2 to the negative x, right? Or 2 to the negative x, 1/2 of x. If we do those same 5 values, that means I'm just going to flip these 4. Let's do that. 1/2 to the negative 2 would be the reciprocal of that. That's going to be 4. That means this one is 1/4. 1/2 to the negative 1, I flip it. That just gives me 2, which means 1/2 to the first is 1/2. Anything to the first power is 1. I've taken this column of my x values, or my f of x values, and I've flipped it over, reversed it. That is going to be true as I work my way through. My second one that we would look at, f of x equals 3 to the negative x, which is the same thing as 1/3 to the x. When I use those 5 values, it's going to reverse that order. Now, 1/3 to the negative 2 is 9, and 1/3 to the positive 2 is 1/9. 1/3 to the negative 1 is 3, and 1/3 to the positive 1 is 1/3. Anything to the 0 power is 1. And then finally, f of x equals 1/10 to the x, which is the same thing as 10 to the negative x. Notice my x values, my inputs aren't changing directions, aren't changing order. What changes order is my output, my y values or my function values. Still have the same y-intercept. It's just that, and I still have the same horizontal asymptote. It's just that I'm moving in the other direction. Instead of increasing with each of those functions, I am decreasing with each of those functions and values. Functions that show exponential decay. All right. My pattern of transformations for exponential functions is the same pattern as for polynomial functions. And like I've mentioned before, it's going to be the same pattern for all types of functions, all the way through trig functions. If you stay in, go to trig and pre-cal, or business calculus, you're going to see trig functions following this same pattern, where we have a reflection across the x-axis shows out front with a negative, reflect on the x-axis. Coefficient would be a vertical stretch or shrink. Stretch or compression, shrink's easier to write. H is my horizontal shift still, and that horizontal shift is still attached to x. It's just that now x is my exponent. And then K is my vertical shift, still added on at the end, or it could be at the beginning, tacked on at the beginning or the end, but it's just kind of added on. My vertical shift goes the way I expect it to. My horizontal shift is still going to be opposite the way I expect it to because it's a negative there. Now I have 3 functions, g, h, and m. It's asking for the parent function. Well, my parent function is going to be the same base. So my parent function, we're going to do f of x equals 3 to the x. And we've already graphed that parent function right here. So we already know what it looks like, and we know what our 5 main points are going to be. So I've got a horizontal asymptote at 0, y equals 0. It's going to go through the intercept 0, 1, and it's going to increase, let's say, about that steep right there. There's my parent function. My domain is all real numbers. My range is limited by that horizontal asymptote to 0 to positive infinity. Now, anytime you've got all real numbers, starts all real numbers, stays all real numbers, remember that. My range is from 0 not inclusive to positive infinity. Okay, let's do some transformations. Right here, g of x is 3 to the x plus 2, so that's my horizontal shift. It says x plus 2, but since it starts as x minus, that means I'm shifting to the left 2. Well, what's going to shift to the left? this intercept is going to shift to the left. So where my parent function has an intercept at 0, 1, if I take that back to the left, it's going to be at -2, 1. I'm just moving left, right. I'm not moving up, down, which means my horizontal asymptote is going to stay where it was. It's not going to move. And I want you to notice, and I try to sketch the same curve as I did. I want you to notice that my horizontal asymptote is absolutely part of the graph that I expect. My horizontal asymptote is still at y equals 0. My domain is still all real numbers. That's always going to be the case. My range didn't change because my asymptote didn't change and my direction didn't change. All right, next transformation, h of x, 3 to the x plus 2. Now this plus 2 this time is not up here attached to the x, it's just tacked on. So this function is going to go up 2 units. Now if it goes up 2 units, that means everything shifts up. So my horizontal asymptote moves up, my intercept moves up. My asymptote is going to go up 2, so instead of at 0, now my horizontal asymptote is at y equals 2. My intercept was at 0, 1, it goes up 2, so instead of 1, it's at 1, 2, 3. So 0, 3 is where that asymptote goes, and then I try to sketch the same increase. So when I compare it to my parent function, it has moved up 2 units. My domain, all real numbers, stays all real numbers, but that range has sure changed. Instead of being limited at 0, now it is limited from 2 to positive infinity. And then my final transformation, m of x is -3 to the x. This negative out front reflects it across the x-axis. If it's just reflecting, I'm taking my parent function, I'm flipping it upside down. Instead of existing above the horizontal asymptote, it exists below the horizontal asymptote. The horizontal asymptote is not moving, so my horizontal asymptote is still at y equals 0. My y-intercept, instead of being a 0, positive 1, is now 0, -1. And then I try to sketch the same curve, but now it is a decrease or a decay function instead of an increase, an exponential growth function. Domain, still all real numbers. My range has changed. The limit is still 0, but now that's the upper limit instead of the lower limit. So my range goes from -infinity up to 0. All right, there is a good overview and look at our pattern of transformations. Let's see what else we have. We've got one more page to get through here. Many real-life situations can be described using exponential functions, including population growth of people, animals, microbes, different types of populations, growth of epidemics, COVID, radioactive decay, when you're taking science classes, and other changes that involve rapid increases or decreases. Sometimes these changes are modeled using what we call the natural base. Now, my natural base is the irrational number e. You know another irrational number that's on your calculator. You're used to using pi, which is another irrational base. Pi is 3.14 is our approximation, but that's not pi exactly. Pi exactly goes on forever. That's the definition of an irrational number. It's going to go on forever with no repetitions. In our calculator, if we push pi, we get it cut off, but that's just because we run out of space on our calculator. The natural base e is the second function, base e is the second function of ln, which is my natural log. So let's clear this out. We're going to do second function ln to pull up e to the power. Well, we're just going to do e to the first power so we can look to see what e is worth. Well, e, again, irrational number, so it's going to extend forever without repetition. Without a pattern, without repetition, without ending. But we need something that we can round it to and use. So when we talk about e, we talk about it as 2.72. Just like we talk about pi as 3.14, we're going to round e to 2.72. Now we don't use the rounded value of e unless we're told to. We use the button for e. What's the other irrational constant? Well, that's pi, and we usually round pi to 3.14. Okay. We introduce that base e because we use it when we talk about compound interest, interest that's compounded continuously. This is my compound interest formula. You notice it's a little bit more complex. Compounded continuously, it looks a little more simple. It uses e. You don't have to memorize these functions. You will be using them a lot this semester, but I'll always be giving you the equations. You just have to know what to plug in. A is the final amount in an account for either one of these. P represents the principal. Principal can be what you invest or what you borrow, depending on which way you're moving money. R is the rate. Usually it's given as an annual rate, as a percent. You're always going to use it as a decimal though. N is the number of times something is compounded. And T is time, how many years we're doing it for. Okay, so let's do some calculator math. We're going to do some examples with our calculator. You're given $10,000 by Aunt Gerda and decide to invest it at an annual rate of 5.5%. How much money will be in the account after 5 years if it's compounded monthly? So our principal, the amount we're investing, is going to be the $10,000 we were given. Our rate is 5.5%, but we're going to turn that into a decimal to work with it. We're going to move that decimal 2 places to the left. Percent means per 100. So if I take my 5.5 and divide it by 100, it moves that decimal 2 places to the left. My time is 5 years, and my compounding period, N, is monthly. Well, how many months are there in a year? There are 12. So I'm going to use my compound interest formula right here. I'm solving for the amount in the account. So I'm solving for A, where my principal is 10,000. I have 1 plus that rate as a decimal over 12 for compounded monthly. And we're doing 12 months a year for 5 years. So this exponent tells me how many times I'm going to compound the interest. 12 times 5 is 60. Now, order of operations absolutely matters. I don't trust my calculator to do order of operations correctly because I tend to forget exponents. So I always do it in chunks and hit enter. I'm going to start on the inside of my parentheses. 0.055 divided by 12. That gives me this decimal. I need to add 1 to that because that's also inside my parentheses. Notice I'm not rounding this off. I'm leaving it there. Before I multiply by 10,000, that's the last step. Before I multiply by 10,000, I need to raise this base to my exponent. We've got 2 choices. I can either say, you know what, 12 times 5 is 60 and raise this to the 60th power, or I can put 12 times 5 in parentheses as my exponent. Here's my base. I'm going to push my exponent button. That base is this answer that I just had. Raise to the, if I want to multiply, my calculator multiply it together, these numbers have to be in parentheses. Otherwise, it takes that first number as my exponent and then multiplies that value times the next number. So my answer raised to the exponent, 12 times 5, I hit enter. That's all of this part. Now I need to multiply that times 10,000. Again, I'm not rounding it off. I'm just going to say times 10,000. Let my calculator do all the work of keeping the values straight. And now it's money, so I'm going to round it to the nearest penny. 2 decimal places. Find the 3, look to the right. It's more than halfway there, so it's going to round up. So at the end of 5 years, at that rate in compounding period, I will have $13,157.04 in the account. What if it's compounded quarterly? Well, how many quarters are there in a year? There's 4, so instead of n equals 12, now n equals 4, and everything else is the same. So it's divided by 4, and then 4 times 5 is my exponent instead of 12 times 5. I'm going to give you the answer on that. Go back and look at the last problem if you need to see how to put that into your calculator. Notice that when I don't compound it as often, it's only n is 4 instead of 12, the amount in my account goes down a little bit. compounded continuously, we go all the way up to daily. But if we want to do compounded continuously, we use our other formula, which is a simpler formula. P equals e to the RT power. If it's compounded continuously, we're still using the same rate, the same time of 5 years. So we have A equals 10,000 to the e to the 0.5055 times 5, because it's being compounded for 5 years. So that's my exponent. I do e to that power first, and then I multiply by 10,000. So back to your calculator, e is the second function natural log. So I do second function ln, brings up e to the power. Notice it sets up your parentheses for you, which is nice. There's my exponent. Get that answer, and then I need to multiply that by 10,000. I forgot I didn't hit my times. Okay, it's good to have a mistake. All right, I saw that, I knew that was the wrong answer, so I went back to e to the power 0.055 times 5. My times button didn't hit last time, and I didn't notice. Times 10,000. There we go. This is the amount in the account if it's compounded continuously for 5 years. And notice that this is a little bit more than if it were compounded monthly. All right, one more question here where we are going to do calculator math again. Give you a second to read the problem. We're given a function. Represents the energy produced from dry natural gas. It's in trillion cubic feet, where T equals 10 corresponds to the year 2010. If we're asked to find the amount of dry natural gas energy produced in 2000, T is going to be 0. Well, what is anything to the 0 power? It's just 1, right? So if I'm finding G of 0, I've got that 14.66 and then 1.042 to the 0 power. This is just 1. Well, anything times 1 is just itself. So I would have 14.66 trillion cubic feet. It's kind of my starting place. Where x is 0, that's my y-intercept on my graph. Find the amount of natural gas energy produced in 2015. Well, in 2015, T is going to be 15. Do 1.042 to the 15th power first. And then I multiply that times my constant, my vertical stretch, 14.66. And I find out the amount of energy in 2015 from natural gas, dry natural gas, came out to be 27.17. Now we're going to keep our rounding consistent, the 2 decimal places. And that's still in trillions of cubic feet. That matters. 27.17 is wrong. 27.17 trillion cubic feet is my answer. And then finally 2022. So we're finding the value of the function where t is 22. Plug that into your calculator and you should get, make sure that you used your units and make sure that you put it in trillions.